Howdy folks, Mr. Reed here, and welcome to One More Question. So what I'm going to be taking a look at right now is solving a trig equation, specifically one that has the setup so that it's more natural to solve it in degrees. So the type of trig equation that I'm going to be taking a look at right now is kind of a medium level. It's going to be a transformed trig function, but it's not going to have anything real fancy to go along with it. So this is a really good spot if you're kind of getting into the thick of solving trig equations. We're going to be doing a good example of that. So if that's what you want to see, you're in the right place. So let's get to it. Okay, I have above me, solve the following trig equation for all values of x. 2 is equal to, and this is pretty much a fully transformed trig function. So I have vertical stretch, I have a horizontal stretch, I have a horizontal translation. I was going to call it a phase shift, but then I realized I hadn't been using the trig words for the other ones. And we have a vertical translation as well. So I like to start things off by making sure I can see what I'm working on. So 2 is equal to 7 cosine onto 4 onto x minus 10 degrees. There's my hint as to how I'm going to phrase my answer. So I have part of this description being in degrees, so it's really awkward to change it over to radians on whoever is asking me this question. So I'm going to keep things in degrees. So let's go ahead and get started. So goal number 1 is going to be to isolate for the trig statement. So I have cosine of some stuff, but I also have the times 7 at the front and minus 3 at the end. We're going to put those parts together. So I'm going to add 3 to both sides and give me 5. And then I'm going to divide both sides by 7, so it gives me 5/7. And that's going to be equal to the cosine of 4 onto x minus 10 degrees. Now, that is an important place to kind of pause, because I need to get at the x value, which is stuck inside of my trig function, which is a cosine function. So in order to do that, I'm going to need the inverse cosine. I either know this is a special ratio, 5/7, which it isn't. Not one of the ones I know anyway. So I'm going to grab my calculator. Now, I have to make sure my calculator is set in degrees. It is, so I'm going to put in the inverse cosine of positive 5/7, and it's going to tell me it's, that was actually relatively close to a special angle, but I didn't recognize it. Not that it matters, it's not one. We would get here that the angle, which is the entire argument, is equal to about 44.4 degrees. My calculator's telling me 0.415. I'm going to go to the nearest tenth, and I'll be happy with that in this case. Now, if you've done some of these before, you know that this isn't the only possible answer. Actually, every coterminal angle to 44.4 degrees is going to be valid. So how do we write that? Well, we just put every coterminal angle. This has, if we're talking about like the standard angle, if we think of this as just being some angle theta, then my angle theta is just equal to 44.4 degrees plus full rotations of that, which are going to be 360 degrees times k, where k is an element of the integer number system. So that's going to give me a complete set of solutions that have to do with the value my calculator gives me. Sadly, the calculator only gives you one of the valid locations within a single rotation. It doesn't give you both. At least mine doesn't, and then most that I've worked with do not either. So how do we tell where that next one is? Well, we found the 44.4 degrees, which is about this angle right here. What we would discover actually is that happened because cosine was a positive 5/7 to begin with. So that makes sense that we have an angle in this quadrant because my cosine values, x values, are positive there. The other place where I'll have positive x values would be in quadrant 4, so I'm going to be down here. My reference angle is going to be the same, so actually the easiest way to write that next line that I'm going to look at in a moment would be the exact same angle is going to be equal to, or my argument, my whole thing together, it's going to be equal to negative 44.4 degrees, because that's probably the easiest way to refer to that negative rotation. I could go all the way around and say that it's 44.4 degrees less than 360, but I like the negative showing up here. It doesn't give me any weird feelings, so there we go. 360 degrees k. K is an element of integers. All right. So I don't actually have final solutions here because I want to solve for x. I don't care what 4 times x minus 10 degrees is, really. So let's go ahead and do that. I'm going to divide both my sides by 4 to leave me with x minus 10 degrees is equal to, ooh, that worked out really well with the rounding. So 44.4 degrees divided by 4 will give me 11.1 degrees. But I have to divide the whole right-hand side by 4, so I'm going to get as well 90 degrees, still times the k, where k is an element of the integer number system. I'm going to keep going and add 10 degrees to both sides of my equation and get that x is equal to 21.1 degrees plus 90 degrees times k, where k is an element of the integer number system. So that is one of my lines of solutions. So what I'm saying with this answer is that 21.1 degrees should work in the original equation. So should 90 more than that, or 2 times 90 more than that, or 3 times 90 more than that, or negative 1 times 90, or negative 2 times 90. And I would want to say more than that, but because it's negative, it's going to go in the other direction. So we would have an infinite set of answers that correspond to this 21.1 degrees for the x, also going in rotations of 90 degrees now. That actually makes sense. If we look at the original statement, we have a b value of 4, which means a stretch factor of the reciprocal of 4, which is a quarter. If we take the original period of 360 and divide it or multiply it by a quarter, we are going to end up with 90-degree rotations, which is what's showing up in the algebra. Super cool, works out really nicely, and so there's one line of solutions. Our second line of solutions is going to be as well. We'll divide 4 as our first step, and it will give us negative 11.1 degrees. Adding on as well, 90 degrees times k, where k is an integer. And then I'll add 10 to both sides. And in adding 10, it kind of goes in the other direction this time. So it's not negative 21.1. It actually becomes just negative 1.1. So be careful when setting these sorts of things up that you don't just copy what you have for your other line. Actually work the algebra through and make sure you're on the right path there. So negative 1.1 degrees. And then because we're just adding 10, we group it together with the part that's just a number. The 90 degrees times k is not touched, and so we'll have that k has to be an integer. All right, so I have my 2 solution lines. If you're happy with that and you don't care about checking or figuring out what's going on, then this combined with this are the final answers to our problem. You're going to get every single possible solution by following these 2 lines that we've created, these 2 lines of solutions, not linear equations. So one of the things that I like to do, at least show my students, is that you can take a random value for k, take one of these lines and test it into the original to see if it kind of makes sense. So I'm going to grab a trusty old calculator here, I guess, because I'm not going to be able to check this properly without it. So I'm going to take a k value of 17. So I'm going to do the second line that I have, so my bottom one with the negative 1.1. So negative 1.1 plus 90 times 17. I think I said 17 to begin with. If I didn't, that's what I'm using, k value of 17. So that's going to give me 1,528.9 degrees. That's kind of a random angle, but it should be one of the angles that work in the original equation. So I take that as my x value. I'm going to subtract 10 from it. Going to multiply by 4, take the cosine, multiply by 7, subtract 3, and I'm supposed to get 2. I actually got 2.0013, which lines up beautifully with the fact that I already rounded this value and made it not quite precise when I wrote it down as 44.4 degrees. So I'm feeling being off by a little over 1/1000th of a unit is pretty darn good. All right, so that is solving a trig equation in degrees, and we have all of the infinite solutions for it. If this question were to be just a touch different and we had a particular domain, I would do the question identically up to this point and then I would use a few different k values to generate solutions until we got too large for the domain and too small for the domain by taking maybe negative k, or you might not even. So depending on where the domain was, it could be from like 500 to 800 degrees, which would be kind of weird, but that would be okay. I would just add k values that are different until I got to my 500 bottom mark, and then I'd start recording my answers, keep adding 90 degrees, 90 degrees, 90 degrees. Then I might get outside of the 800, stop recording any of my solutions. So I would still do exactly the same thing up to that point. We would just use test k values in order to see what angles will fit inside of what we're told to do. Hopefully you found that one helpful. If you did, like, subscribe, and as always, take care, folks.